Sa video natin ngayon, I will try to discuss the major types of structures, which are beams, trusses, frames, and arches, and then we'll try to look into their purpose and utility. So first, we have our beams. Now click natin. Itong beams are types of structures used in construction to provide a safe and efficient load path to distribute weight throughout the foundation of a building. And so let's try to look at some examples. So ito yan. This part right here, ito yung beam. And then meron siyang kine-carry dito. And then this is also a beam, and it is used to support itong roofing structure. And then yung typical na shape ng beam is I. Now this is because malaki yung moment of inertia na na-provide niya about the x-axis. And so now, let's move on to our trusses. Trusses are structures consisting of linear axial members arranged in triangles and connected at pin joints or internal hinges. So ito yan. Usually, kita natin to sa mga bridges and also sa mga roof natin. And these members right here, they either carry compression or tension. So this is an example of a bridge. And then this is an example of a truss structure na ginagamit sa roof. Now for roofs, usually compression yung dinadala nito. Itong mga members. Kasi what usually acts towards dito sa roof natin are wind loads. And then wind loads act perpendicular to each member. And then wind loads act perpendicular to your structure. And then next, we have our frames, which essentially gives the structure its support and shape. And then we have some examples for that. This is how our frames would look like. Yan. This is an example of a concrete frame structure. And then if we try to look at the whole system, we have our foundations, we have our beams, and our columns. And then itong naka-green saka orange, ito yung slabs natin. And then what we consider as a frame is itong structure na to, ito. It's the combination of columns and beams. For example, this one, and then this connection, and also this connection. That's considered a frame. And also from here, ito tayo nag-view, ito yung frame natin. These are the end columns, itong dalawa. And then ito yung interior columns, itong dalawa dito. And then we have two rows of beams. And then finally, we have our arches, which are vertical curved structures that spans an elevated space and may or may not support the weight above it. Now usually, these structures carry compression. Now let's click on it, and then let's try to look at our examples. Now these are arches because this part right here is curved, and then that's the main characteristic of arches. And then it may also be seen in bridges, and then it's usually at the bottom because there are vehicles right here. Ito yung magki-carry ng compression to support the structure. And then it may also be used in conjunction with other elements. Like for example, these members are mimicking a truss structure. And so now, let's try to move on to the types of loads that we often see in our structures. So ito yan. We have our dead loads, which are loads coming from the dead weights of members such as beams, flooring, columns, or trusses. So ito yung importante dyan. These are the dead weights or the actual weight of the beam itself or the flooring itself. Now usually for beams, this weight is given in kg per meter. Let's say this is our beam and then this is the length. If we multiply this one by the length, then we will be able to get the total weight of the beam, which is its dead load. But then meron din tayong superimposed dead loads, which are loads that may be fixed within your structure, and so it will be added onto the actual weight of the beam. So let's say you have this beam, and then you have the weight of the beam, and then you have another weight which is the superimposed dead load. Pwede din to. Now let's try to tackle this in our problems later. Next, we have our live loads, which are loads coming from fixtures that may be placed in our structure and is due to occupancy. And then it may also change its magnitude and point of application within the life of the structure. Now an example of this one may be the bookshelves in our libraries, the furnitures in our offices, or other things that may be added to our structure. And then for bridges, what we usually consider as live loads are the vehicles, because these vehicles move along the bridge, and then their point of application changes with time. Because for example, you have this bridge, and then there's a car right here, and then let's say ito yung front load, and then this is the rear load. If this car moves along the bridge, let's say after some time, andito na yan, ito na yung loads natin. Ito na yung front, and then ito yung rear. And so that's why it's called a moving load, because the point of application changes within the life of the structure. But usually this just happens in seconds. And then we also have our wind loads, which act perpendicular to the surface areas of our structure. Let's say this is our roof. Our wind loads will act perpendicular to the surface area of the structure, so it will act this way. This is our wind load, which acts perpendicular to this line. Now sometimes wind loads may also cause a suction pressure, and so it will act like this. This is the suction pressure. And then we may also consider from the leeward side or the windward side. And then usually we'll encounter this one when we are dealing with purlins, which are essentially beams spaced evenly across our roof structure. And then whether or not leeward or windward side siya, it depends on the wind zone of a specific country. And then we also have our earthquake loads, which are loads produced by earthquake or seismic movements of the ground. Now usually earthquake loads are considered as lateral loads. So let's say you have this frame structure, this is your footing, and then these are your columns, and then these are your beams. So earthquake loads will act like this. And we may also consider a base shear force. This is usually tackled in our earthquake engineering. And then we also have our hydraulic loads, which are usually seen in our dams. So let's say we have this dam structure, and then it's used as a control structure to contain water here. This water will have a resultant horizontal force acting right here because this is its stress distribution. And then let's say this is P. Itong P, this is the total load exerted by the water due to water pressure or hydraulic loads. And we may also see this in tanks wherein we have circumferential and longitudinal stresses due to water right here, because this water has its own weight, and then it also causes pressure at the sides of the tank, let's say right there. Now this is already discussed in our mechanics. And then we also have snow loads, which are weight coming from snow or ice. And then what's different here from the wind loads is that snow loads usually act downward because it's just an additional weight. So let's say we have our roof structure, and then let's say there's snow right here. It will not act perpendicular to the structure. Instead, it will act vertically like this. And so that's why we also see in our frame problems in statics and mechanics loadings like this, which are not perpendicular. That just means that there's additional weight, let's say coming from snow loads or the like. And then we also have impact loads found in elevators, vehicles, cranes, and the like, which entails the instantaneous application of load. And then this may also be seen in beams subjected to impact loadings. Let's say something fell from this height, and then this is our beam. If this strikes the beam at this point, then that will be considered an impact load. And then usually we just consider the static deflection and then multiply it by the impact factor. But hindi na to lumalabas sa board exam. Maybe only sa undergraduate na studies. And then we also have our soil pressure, which is the pressure applied by the soil or earth on structures such as in retaining walls, footings, dam, foundations, piles, or the like. Now our retaining walls usually look like this, and then we have a soil dito. This is the soil, and then it will exert a pressure dito, which is ganito yung distribution. And then for footings, let's say we have this footing, and then we have our column, and then usually loads are transmitted to the columns. So let's say we have this one. Our footing stands on soil, and so the soil will have a uniformly distributed reaction throughout the span of the footing. So let's say this is the soil will react this way. The soil is just essentially a support that has a uniformly distributed reaction. And then we also have thermal loads, which are produced when some metals such as steel are restrained from deforming freely when temperature changes. So usually we have a fully restrained structure, and then let's say this is steel, and then let's say the temperature rises. If the temperature rises, then this body will expand, and so if this isn't restricted, it will elongate this way in actuality. However, because this member is restrained from moving or deforming, this portion will be subjected to stress or thermal loads. And then if the temperature decreases or declines, then this will shorten. Let's say this way. It will actually shorten at this distance, but since it's restrained from moving or deforming, this part will still be subjected to stresses. And so now let's move on to the stability and determinacy of beams. Now beams are structural members subjected to lateral forces or forces acting perpendicular to the length of the beam. And then these forces cause, mali to, cause dapat to. Kasi yung subject natin is plural. Now these forces cause bending or flexure as well as shear on the beam. The axial forces on beams are usually very small and thus negligible. And so in our analysis, we are just considering the vertical forces. Now first, we have to recall that equilibrium is the state of balance of any body. And so if a body is in a state of equilibrium, the summation of all vertical forces and horizontal forces will be equal to 0, and the summation of moments will also be equal to 0 because there will be no net rotation. Now we also have to recall the types of supports. First, we have our hinge support, which has two reactions. Now these reactions are vertical and horizontal. And then we have our roller, which has one reaction, and then this reaction is just perpendicular to the support. And so for this one, this will just be vertical. Now hinges may also look like this, and then rollers may also be drawn as this. And then roller supports may be inclined. So pwede yan maging ganito. Let's say this is a smooth surface, and then we will place our roller here, and then we have a beam. Yung reaction ng roller is magiging perpendicular dito. So pwede din yan. And then we have fixed supports, which have three reactions, one upward, one horizontal, and then another moment reaction, because this restricts rotation. And then itong rocker is just essentially a roller. However, the support it gives is only vertical. And so ito yan. That's why isang reaction lang. And then itong link has one reaction, which is this one. This is the link. If we will consider this member, the one connected to the link, then this link will have this reaction. Ito yung resistance offered by the link applied to this member. And then for cables, it's just the same with the link. However, this will only usually carry tension forces. And so the reaction of this cable, if we consider this member, will be like this, paganyan. And then we also have our smooth surface, in which yung reaction is perpendicular to the surface. For example, this one, let's say this is a member, and then this is the wall, and then this is the ground. If the ground and the wall are smooth surfaces, then the reaction will only be perpendicular to the surface. So it will be like this. This is perpendicular to this wall, and then for the ground, one reaction will also be here. This is perpendicular to the surface of the ground. However, if the surface is rough, or essentially if the surface offers frictional resistance, then there will be two reactions. Now again, yung one reaction dito is just considering one surface. Now for this surface, isa lang yung reaction, and then for this surface, isa lang din yung reaction. However, kung rough, let's say we will consider this point, we will have a reaction here. However, since there is friction, we will also have a resisting force dito. This will act upward. This is the frictional force. Now this will act upward because our body will naturally slide down. This will slide down, and then this part will move to the left. And so since friction resists that movement, this will act upward. And then dito rin, meron tayong normal reaction. And then since this will naturally move to the left, yung frictional force natin will act patungo dito sa right to resist the movement. So ito yung friction. And so that's why for each surface, dalawa yung reactions. Isang normal and then isang frictional. The same dito. Let's just say this is N, which stands for normal. Ito N din, and then this will also be N. Now, the value of N will be the value of F, or the frictional force, will be mu times N, or the coefficient of friction multiplied by the normal force. This is what you have to remember. And then we also have different types of beams according to supports. Now, this is a hinge support, and then this is a roller support. Now, a beam is considered simply supported if it contains supports at each end. So this is the first end of the beam, and this is the right end, and it is supported by a hinge and roller support. And so that's why it's simply supported. And then the reactions for the hinge will be dalawa, horizontal and vertical, and then the reaction for the roller will be vertical only. And then we also have our overhanging beam. Now the reaction will still be the same. However, these portions, itong naka-highlight, these are called the overhanging part, or simply the overhang. Ito, saka ito, and then ito. Kasi meron na siyang free end. And then these parts are essentially just hanging. And then we also have our cantilever beam, which is just a structure that has a fixed support. And so yung reactions natin dito will be tatlo. One vertical, one horizontal, and one moment reaction to resist rotation. And so ito na yan. Vertical, horizontal, and moment reaction. And then we also have prop supports. Now, this type of structure is indeterminate. And we will be able to solve this once we are able to finish all discussions sa beam deflections. Now, these are just fixed supports, itong dalawa. However, what makes this prop are the supports dito. It may be roller or it may be a hinge. And then, these supports are called the prop end. Saka ito din. And then, our reactions will be essentially apat or lima. And then, we also have a fully restrained beam wherein both sides of the structure are fixed. And so essentially, we have 6 reactions for this structure. Tatlo dito sa left side, and then tatlo din sa right. And then we also have a continuous beam, which usually consists of 3 or more supports. And so this is what makes that continuous. And then this beam, let's say we have this one, and then we have a hinge right here, and then tatlong roller supports. This is also considered continuous because our beam spans over 3 or more supports. And then yung reactions natin dito are tatlo sa fixed end and then dalawa dito sa rulers. And so now we will discuss how to compute the stability and determinacy of beams. So ito yung conventional na way. We have our U, which is the number of unknown reactions. We have E, which is the number of equations defined as ES plus EC, wherein ES is the number of static equations, which is essentially tatlo lang lagi kasi we have the summation of forces vertical, summation of forces horizontal, and the summation of moments. And then we also have our EC, which is the equation of condition, and it is affected by the presence of internal supports. Now for internal hinges, EC will be equal to 1, and then for internal rulers, EC will be equal to 2. Now for internal hinges, this is 1 because we essentially have 3 static equations. And then if we subtract the reactions of internal hinges, which are 2, 1 vertical and 1 horizontal, we will get 1. And then for internal rulers, this is 2 because we have 3 static equations. And then if we subtract the reaction of the internal ruler, which is 1, this will be 2. Now, internal hinges are usually drawn this way. We have this beam. Let's say this is simply supported, and then yung internal hinge nilalagay dito. It's just usually a dotted line. And then yung internal rulers naman will look like this. Let's say you have a fixed beam, and then meron kang another beam dito, which is, let's say, hinged. And then to connect the two members, you will add an internal ruler dito. So this is what's considered as an internal ruler. Essentially, naka-sandwich sa dalawang beams. Now, to determine the degree of indeterminacy, we will have to subtract U and E. Again, U is the number of unknown reactions, and then E will be the number of equations. But yung actual equation natin for I is IE plus II, wherein IE is the external indeterminacy, and then II is the internal indeterminacy. However, in beams, because internal indeterminacy is always 0, the indeterminacy is solely external. And so ito lang yung gagamitin natin. Now, for the conditions of stability, when the number of unknown reactions exceeds the number of static equations, the total number of equations, then our beam is statically stable. Now, if our beam is stable, it may be determinate or indeterminate. Now, it will be determinate if the number of unknown reactions will equal the total number of equations. And then, it will be statically indeterminate if the number of unknown reactions exceeds the number of equations that we can use. Because merong isang reaction dyan na hindi natin masusolve. And so, that's why tinatawag yang indeterminate. And then, for instability, our beam is statically unstable when the number of reactions is lesser than the number of equations. Now, sir, what does this mean? So, let's say you have a hinge, and then this is your beam. Diba, this hinge will provide 2 reactions, one vertical and then one horizontal. However, if this beam doesn't have a support dito, diba usually that's a roller support if simply supported. If walang roller dyan, and then I will apply a load dito na downward, then this beam will just rotate. It will rotate freely such that it will become unstable. Now, why is it unstable? It's because the number of unknowns is lesser than the total number of equations, because we have 3 static equations. Now again, E is equal to ES plus EC. The number of static equations is 3, and then we don't have equations of condition because we don't have an internal hinge or ruler, and so this will be 0. So E will be equal to 3 plus 0. Now 3 is lesser than the number of unknowns. The number of unknowns is 2 because dalawa yung reactions natin, and so this will be 2 is lesser than 3, and so that's why it will be unstable. But if you look at it conceptually, ito yung reason talaga dyan. What will resist the moment or the rotation if walang roller dito or walang another support. Now, we can determine instability using this equation. However, some beams will be determinate. However, they may have a possibility na geometrically unstable sila. Now, this will happen when the beam has concurrent reactions or parallel reactions. Now, sir, what do you mean by concurrent reactions? Concurrent reactions will happen when the line of action of the support reactions will meet at a common point. So, let's say we have this roller support and then another roller support dito. And then let's say the same yung inclination nilang dalawa. And then let's say we have this beam. Now, yung reaction natin dito will be paganto, perpendicular to the surface, and also this one. Now, if we extend this line and also this line, then they will meet at a common point. And so that's why it's geometrically unstable. And aside from reactions, if the force also meets this point, the beam will also be unstable. For example, you have a load here that's applied this way, and then if you extend the line of action, it will meet this point. That's still geometrically unstable due to concurrent reactions. Aside from that, our beam may also be geometrically unstable if all of the reactions are parallel. Now, it will happen when, let's say you have this beam, and then you only have roller supports. Let's say this one. Or it may also be just a simply supported beam with two rollers. Now, if we apply a vertical force only, then these beams will be able to resist that force. Now, the condition that we call this is unstable equilibrium. Now, it's called unstable equilibrium because essentially our beam is unstable. However, the beam will be in a state of equilibrium because of the force that we applied. However, let's say I will apply an inclined force. Let's say this one. Diba? This will have a horizontal component and a vertical component. Now, if the reactions at the roller supports are upward, then it can resist the vertical component of P. However, what will resist itong horizontal force? Diba? Wala. And so that essentially means that if I will apply an inclined load, then itong beam will just move freely to the left. Diba? And then, for this one, if I will apply a horizontal load, then my beam will freely move to the right. Now, if you will solve this one, diba, our number of unknowns will be tatlo. And then, our number of equations will be tatlo rin. Kasi diba, this is U, and then this is E. And then, E is equal to ES plus EC, wherein our ES is 3, and then our EC is 0 because wala tayong internal supports. And so, diba, if we will solve for this beam, it will be determinate according to this solution. However, it is still unstable because of the parallel reactions. Now, again, yung reason dyan is because walang magre-resist sa horizontally applied na load. That's why magiging unstable pa rin yan. Again, ito yung unstable equilibrium. It is a condition where a beam does not regain its original position upon experiencing an external force. Kasi diba dito, sa previous example natin, this beam will be in an unstable equilibrium when a load is applied only vertically. However, it is still essentially unstable, but just because of this configuration, it remains in equilibrium. Now, for the loads on structures, we have a concentrated load, which is just one load, and then we have a uniformly distributed load which acts over a span. Now, this is usually labeled as W, and also this one, and then this is M. When we talk about uniformly distributed load, it's just a load that's applied constantly over a whole span. However, we also have a linearly increasing or decreasing load. Now, this is an example of a linearly increasing load because the load starts from 0, and then up to a certain point, the load will increase into W. And then we also have a linearly decreasing load, which is this one, because the load starts from W and then it will uniformly decrease until it will reach 0. Now, these are just essentially triangular loads. And then we also have a moment load. Now, this moment load doesn't affect our shear diagram, but it will affect directly our moment diagram. Now, to internalize the stability and determinacy of beams, I have here 14 examples. And then I will also teach you how to apply the alternative formula, which is R equals 3n. N. Now, this can be applied to determine the stability and determinacy of beams. However, this R considers all reactions, including internal reactions. So, all reactions, including internal. This is different from U equals E because U here only considers external reactions. And then, yung N natin dito is the number of members. So, for this example, we have a hinge and a member wherein our external reactions are 2, and then our number of equations will be ES plus EC. again, this is ES plus EC. Now, ES is equal to 3 and then EC will be equal to 0 because wala tayong internal supports. And so since U is lesser than E, the beam is statically unstable. However, if we use this formula, we can directly write, again, R is equal to 3N. Now, the number of reactions, total reactions will be 2. And then we will equate this with 3N. Now, the number of members is just 1. So, 3 times 1, we will have 2 is lesser than 3. Now, if the left side is lesser than the right side, then our beam will be unstable. Again, the result of this one will not always be the same with the results of this one in terms of numerical value. However, what we are interested in is only the difference of the two sides. So, the difference of the left side and the right side. Now, for this example, this will be in unstable equilibrium because the beam is geometrically unstable due to parallel reactions. However, it is in a state of equilibrium because the loads are only vertical. And then this one will be geometrically unstable because all reactions are parallel. Nothing will resist the horizontal component of this force. And then for the next one, we have a geometrically unstable beam due to concurrent forces because all of these forces, these two and the reaction forces meet at a common point. Now, this is stable and statically determinate because we have 3 reactions here, 2 for the hinge and then 1 for the roller. So our U will be 3 and then our E will be ES plus EC, wherein our EC will be 0 and then ES will be 3. So U is equal to E because 3 is equal to 3. Now, applying R is equal to 3N, we have 3 reactions and then the number of members will be 1 and so 3 is equal to 3. And so that's why it's determinate. Now, for this one, we also have a determinate beam because we have 3 reactions here, 1, 2, and then a moment reaction. And so our U is 3 and then our E is also 3, and so our beam is stable and statically determinate. Applying R is equal to 3N, we have 3 reactions is equal to 3 times 1 member. So 3 is equal to 3, which matches the difference of the left and right side of this equation and also this one. And then for number 7, we have a prop beam. Again, as discussed, this is the prop end. Now, this will have a vertical reaction and then we will have 3 reactions dito. And so that's why our R is equal to 4 and then our number of members will be 1. R is equal to 3N, we have 4 is greater than 3 times 1. Now, 4 minus 3 is equal to 1. The difference between R and 3N is the degree of indeterminacy. So, I is equal to 1 degree. And so, again, the difference between R and 3N is the degree of indeterminacy, I. If the if the difference between R and 3N will come out to be negative, then that means that your beam is unstable. Again, let's go back to this example. Now, the difference between R and 3N will be 2 minus 3, which is negative 1. And so, since this is negative, that means that your beam is statically unstable. Now again, this beam is stable but statically indeterminate. Now for this one, we have our U, which is 4 because again, U only includes the external reactions. Now these are the external reactions 1, 2, 3, and 4. And so that's why our U is 4 and then our E is 3 plus 1 because ES is 3 and then EC is 1. Now this is 1 because we have the presence of an internal hinge. And so that's why this is stable and statically determinate because equating U and E, we have 4 equals 4. Now, if we will use R is equal to 3N, then we will consider all reactions. Now, R will include the internal reactions. The internal hinge will have 2 reactions, 1 vertical and 1 horizontal. And so our R will be 1, 2, 3, 4, 5, and 6. And so we have 6 reactions in total. And then our number of members, again, because there is an internal hinge, our number of members will be divided into, our member will be divided into 2. And so our number of members will be 1 and then 2. So this will be 3 times 2. And so 6 will be equal to 6. And so our beam will be statically determinate. Now this is what I meant kanina na yung result natin sa using U is equal to E and then using R is equal to 3N may be different. However, if we will subtract the 2, they will just equal 0. And so, essentially, we will just be comparing yung mga differences nila. 4 minus 4 is equal to 0, and then 6 minus 6 is equal to 0. And so, yung conclusion mo will still be the same. Hindi magmamatter kung ano yung numerical value dito, saka dito. Now, for this one, we have 3 reactions. And then, solving this one, diba, R is equal to 3n. We will have 3 is equal to 3 times the number of members, which is 1. It will be considered as determinate. However, this is geometrically unstable because all the reactions are parallel. Nothing will resist the horizontal component of this inclined load. Now, for this one, we have 2 reactions for the hinge and then 3 reactions at the fixed support. And so, our R will be 5, and then our number of members is 1. So, R is equal to 3n. We have 5 is equal to 3 times 1. And so, 5 minus 3, or the difference between R and 3n, will be the degree of indeterminacy, which is 2 degrees. And then you may also use U is equal to E, wherein U is equal to 5, and then E is equal to ES plus EC, which is plus 0. Now, if you have this figure, you will have 2 reactions at the hinge support and then 1 reaction at the link support. And so, our R will be 3, and then our number of members will be 1. So, R is equal to 3n. We have 3 is equal to 3 times 1. So, 3 is equal to 3, which means our beam is stable and static. And then for the next one, we have a continuous beam. Now, we have reactions here, and then 1 dito, and also dito. So, we have a total of 4 external reactions, and then our number of members is 1. And so, our I will be R minus 3n, which is 4 minus 3. And so, we will have 1. So, our beam is statically indeterminate to the first degree, and then it's stable. Next, we have this one, fully restrained beam. Now, this will have 3 reactions dito, and then 3 reactions din dito. So, our R will be 6, and then our number of members will be 1. So, 6 minus 3, that will be our I, which is 3 degrees. So, our beam is statically indeterminate to the third degree, and it is stable. And then if we have this structure, this will have a reaction here, and also here, and also here. And so we will have a total of 3 reactions, and then we have 1 member. So using R is equal to 3n, we have 3 is equal to 3 times 1. And so our beam will be stable and statically determinate. Now, sir, what if you have this structure, the one you have drawn earlier, wherein you have a fixed support, and then a roller support here, an internal roller, and then another beam here with a hinge? How will we determine the stability and determinacy of this one? So, again, you can apply U is equal to E or R is equal to 3n. Now, this beam, using U is equal to E, we can write the external reactions. Now, this will have 3 reactions here, and then 1 here. I mean 2, because this is a hinge. And then, if you will use U is equal to E, you will not consider this one because this is an internal roller that will have an internal reaction. And so, your U will essentially be 5. And then your number of equations will be ES plus EC, wherein ES is 3 and then EC is 2, because again EC is 2 for internal rollers. And so this will be 5 is equal to 5, which means that this structure is determinate. However, if you will use R is equal to 3n, you will include this internal reaction. Now, this roller support, this internal roller will have a vertical reaction. So we will include this one because this is the internal vertical reaction of this roller support. And so our R will be 3 here, and then 2 dito. So, 3 plus 2, 5, and then plus 1 dito. So, this will be 5. Magiging 6. So, 6 will be equal to 3 times the number of members. Now, we have 2 members, 1 here and 1 dito. So, the number of members will be 2. And so, 6 will be equal to 6, which means that our beam is determinate and stable if this is the structure. Sa video natin ngayon, I will be discussing the types of beams and also the transmission of loads from beams to columns and then to the footings. So first, we have our types of beams, which actually entail a lot, but let's just focus dito sa mga common. First, we have our joists, which are smaller beams closely spaced and supports the flooring, ceiling, or roofs. So ito yan. This is our joist hangers, and then this is our ceiling joists, and usually they are evenly spaced to carry the ceiling. And then this one right here is the beam, and then the beam essentially carries the joists. However, fundamentally, joists just act as beams. However, joists are much smaller and much more closely spaced. And then next, we have our girders, which are large beams, usually supporting the joists or connected with other smaller beams. And so ito yan. We have our joist, these right here, and then the joists are carried by the beams because this is our floor beam. And then the floor beam is carried by the girder. Now, itong girder is naturally larger than the floor beam and the joist because ito yung nagkikarry ng essentially lahat ng to. And then girders span substructure to substructure. And then we also have girts which are attached to the post or columns supporting the flooring system or roofing. And so ito yung itsura ng girt natin. And then we also have lintel beams which are placed over openings such as doors or windows. And so ito yan, this type of beam. Now perhaps this is the entrance of the building. And then we also have purlins na usually talaga lumalabas sa board exam, and then they are flexural members inclined from the horizontal and supported by trusses. So beams pa rin to, and then they are closely spaced within sa roofing system natin. So ito yung itsura niyan. We have a truss here, ito, and then these trusses are evenly spaced. Ito, first truss, and then second, third, and so on. And then within this span, we have our purlins. Ito yung purlins natin. Ito, saka ito, and then ito. And then they are evenly spaced. Usually, yung kinakalculate sa board exam is yung spacing ng purlins or yung mga stresses. Kasi meron kasi itong bending about X and about Y. Now, perhaps we can tackle that later. And then we also have rafters, which are beams placed above and perpendicular to the purlins for roofs with sheathings or serve as a support for purlins for rafter type roofs. Now, rafters are used when our roofs don't have trusses. And so ito yung rafter natin. Itong dalawa. And then we also have stringers, which is found in steel bridges, and they are the large steel beams supporting the concrete pavement running parallel to the direction of traffic. And so ito yung system natin. We have our floor beams, ito, and then we have our stringers. Now, para lang itong joists talaga. However, it's applied dito sa steel bridges. And so again, ito yung floor beams. They support the stringers and transmit the traffic load to the bridge truss. Again, this will carry a load. This will carry a load, and then it's essentially carried by the floor beam, and then itong floor beam will act as a load dito sa joints. Now, diba, if you want to think of it conceptually, when we solve for trusses, usually there are loads dito sa joints natin. For example, this is our truss. Ito, merong load dito, and then dito, and then dito, and so on. Now, those loads come from the reactions dito sa floor beams due to load transmittal. And so, hindi lang talaga yan nilalagay for just for fun or just to create your problems. Loads are usually at these joints due to real-life situations. And so now, let's move on to load computations. First, we have the dead load of beams. Now first, we have the distributed dead weight of beams, which is equal to gamma times A. Now, itong gamma is the unit weight of the beam material. For steel, it's 77.01. Now, these values are constant, and then for concrete, it's 23.54, or usually near-round up to 24, and then for wood or lumber, for timber design, it's 5 to 9 kN per m cubed. And then itong A is the cross-sectional area of the beam. Now sir, why are we multiplying this by the area? Diba, yung unit weight is kN per m cubed. And then diba, if we multiply this by the area, which is in meters squared, diba, magka-cancel yung m squared, and then merong isang m na matitira dito. And so diba, itong kN per m, this is the distributed dead weight. That's why we will multiply this by the area if gusto mo yung unit analysis talaga. And so we have an example right here. Let's try to compute for the dead load. Compute daw the distributed dead load. Now usually WB yung label ko dito, which just means na weight of the beam. So W beam of a 75 mm by 150 mm wooden floor joist if lumber weighs 5.5 kN per m cubed. Also compute the total dead weight of the wooden joist if it is 3 meters long. So first, let's try to draw our beam. Meron daw tayong beam na 3 meters long. Napagpasensyahan nyo na yung drawing ko kasi wala akong ruler dito. Hindi kasi to one note. So let's say we have this beam, and then this is 3 meters. Now usually yung beams natin are simply supported. So let's just say merong hinge dito, and then dito merong ruler. Now, if dito tayo mag-view, dito, yung cross-section yung tinitingnan natin, the beam will look like this. This is the cross-section of the beam. And then yung dimensions natin is 75 by 150. And so ito yan, 75 mm by 150 mm. Now, yung distributed load dito will act over the span of the beam. So ito yan. Let's say this is WB, or the uniformly distributed load ng beam na to. In 3D, ganito kasi yung itsura ng beam natin. Yan. And so we will multiply this by the unit weight. So WB will be equal to 5.5 kN per m cube multiplied by this area so that we can convert it into kN per m. Dito rin galing yung mga computations natin sa mechanics. Again, WB is equal to gamma times the cross-sectional area. So the cross-sectional area is 75 by 150. So this is 75 mm times 150 mm. Now this is m cubed. And so we will have to convert these units. Kasi mm kasi yan. And so mm times mm magiging m squared. And so we will just multiply mm dito so that magka-cancel to. And then since dalawa yan, we will square the whole expression. Now, 1000 mm pala. 1000 mm is equivalent to 1 meter because we need to convert this into meter. So kaya m yung nandito and then yung nasa baba is yung mm para magka-cancel to. And so since we are squaring this one, this will cancel and then dalawa yung magka-cancel dito. And so now we can compute for WB. So we have WB is equal to 5.5 times 75 times 150 divided by 1000 squared. And this will equal to 6.1875 times 10 to the power of -3. However, this is still in kN, kN per m. We need to compute the total dead weight of the wooden joist in newtons. And so, we will have to convert this into newtons. To convert this into N per m, ito yung gagawin natin. 6.1875 times 10 to the -3, this is in kN per m. And so, we will multiply this by 1000 newtons is to 1 kN para magka-cancel to. And then, we will have our unit in Newton per meter. So, 6.1875 times 10 to the -3 multiplied by 1000 will give us 6.1875. And then, this is in Newton per meter. This is, 0.061875. And so, ito rin, 0.061875. And then multiplied by 1000, we have 61.875. Now, this is in Newton per meter. So, ito na yung WB natin. So, WB is equal to 61.875 Newton per meter. And so, we already have our answer for this one. And then next, we have to compute the total dead weight of the wooden joist if it is 3 meters long. Now, to compute this one, itong total dead weight, we just have to multiply this by the span. Because yung asked sa problem natin is yung resultant na load of this beam weight. So, ito yan. We have a resultant dito. Now, diba, the resultant is just the distributed load multiplied by the span. And so, for the total dead weight, let's just label this as R, or the resultant. So, R will be equal to 61.875 Newton per meter and then multiplied by the span, which is 3 meters. And so, diba, magka-cancel yung meters. And so, we are left with newtons. Yan na yung total dead weight. So, 61.875 times 3 magiging 185.625. And then, this is in newtons. So, ito na yung R na yan. So, this is our answer for this one. And then, for the first question, we have this value. And so, let's try to check. We have our distributed dead load, which is 61.9. And then, our total dead weight is 185.7. And so, the same lang dito. Next, we have to compute the dead load of this beam. So we have now a steel stringer that has the cross-section shown, which is ito. And then if the unit weight of steel is 77.01 kN per m cube, determine the uniform dead load of the stringer and also the resultant or total dead weight if its span is 6 meters. So meron na akong figure para dito. Now this is WB in kN per m, and then ito yung resultant weight. That's why this is capital. So again, we will just use the same formula, diba? WB will be equal to gamma, or the unit weight, multiplied by the area. Now, our gamma will be 77.01. So, 77.01 kN per m cube. And then, we will multiply this by the area. Now, the area of this one cannot be easily computed. We have to look at our figure talaga. And so, I will just separate the computation of the area dito. So, the area of this I section is, let's divide this into 3 parts. This part right here, which is the flange, and then ito rin. Now, itong area na to, this is the web. And then itong top saka bottom, yan yung flanges natin. So this is also a flange. Now, since the dimension of our top and bottom flanges are just equal with 180 by 10 mm, let's just multiply that by 2. And then we will add the area of this web, which is 220 by 12 mm. So again, our area will be 2 times the area of a flange, kasi dalawa yan and equal, plus the area of the web. Now, the area of the flange is 180 by 10 mm. And so we have 2 times 180 times 10 mm. And then plus, close natin to. And then we will add the area of the web. The area of the web is 220 times itong thickness ng web, which is itong 12 millimeters. So this is 220 times 12. And so this will be 6240 and then mm squared. And so lagay natin yan dito. This will be 6240 mm squared. And then let's convert this into m squared. So we will multiply this by 1 meter is to 1000 mm. And since this is squared, we will just square this one para magka-cancel na to. Now, this is 0.4805424. And then yung unit is kN per meter. So ito na yan, 0.48 kN per m. And so to get the resultant or total dead weight, we have the uniform dead load of the stringer multiplied by the span. So this will be 0.48 kN per m multiplied by 6 meters. And so this will cancel and we will have 2.88 kN. This will be our answer for the first question and ito sa second one. And so let's try to check. This is 0.481 and 2.89. So tama yung solution natin. Now, since tapos na tayo sa beams, we will move on to the dead loads dito sa flooring natin. Now, this is how our flooring will look like. This may be concrete or wooden. And then, ito yung spacing ng joists natin. Ito, evenly distributed. And then, ito yung thickness ng floor. Yan. Saka ito. And then, meron tayong tributary area. Now, itong tributary area refers to the total area of the structure that is supported by a particular load. Now, for example, we have this joist. It will carry effectively itong slab na to. Kasi hindi naman pwede na isang joist will carry the whole slab. Divided talaga yan. And so if this is the tributary area of this joist, if we will consider this one, ito yung tributary area niya. And then for this joist, we will have another one here. Yan. Now usually, yung kinikarry ng joist is half ng spacing nito. Again, this is the spacing. And then usually, this dimension is S over 2. If we draw a line dito sa center, this is S over 2. And then, this is S over 2. Or essentially, half ng spacing for each side. Dito and dito. And so, that's why this is S. Kasi diba, this is our spacing ng joists. Baka magtaka kayo kung bakit S pa rin to. Kasi diba, this is a different distance. However, that's just essentially S over 2 plus S over 2. And so, that's why that will equal S. Now, for the dead load of flooring, we will still use the same formula. Diba? Gamma times area to convert it into kN per meter. However, our area will be for the flooring because again, this is the joist. We are not interested in that kasi tapos na tayo niyan kanina. And so we will focus on the flooring. Now, the dimension of the flooring will be the thickness times the spacing. Kasi diba, again, this is the thickness. Ito. And then, this is the spacing. That's why, yung area nito, this is the cross-sectional area, that's T times S. So, balik tayo dito. That's why yung area natin is reduced into S times T. And so now, let's try to solve this problem. A floor system daw consists of a 25 mm thick wooden floor supported by wooden floor joists spaced at 0.3 meters on centers. If the unit weight of wood is 6 kN per m cube, we have to find the distributed dead load carried by each joist. And if each joist is 100 mm by 150 mm and has the same unit weight as the floor, also compute the dead load of each joist and the total distributed dead load that each joist will carry including itself. And so, ito yung drawing natin. We have the a floor which is 25 mm thick, and then yung joist natin is 100 mm by 150 mm, and then our spacing is 0.3, and so this distance will be S over 2, yan, and then ito rin. And so kaya this is S. Now if this is S and this is T, this will be the cross section of our floor. And so to compute for the dead weight of the floor, we have WF, let's just say this is the floor, that's equal to gamma times the area, or simply S times T. Now, our unit weight is 6 kN per m cube. So, sulat natin yan dito. So, gamma is equal to 6 kN per m cube. Now, this is for the floor. However, it's also mentioned dito na the joists have the same unit weight as the floor. Now, if that's different, then you will multiply the joists by another number. But since the unit weights are the same, we will only have 6 kN per m cubed. So, this is for the floor and the beam. If yung unit weight ng beam is different, then it's helpful to label this as gamma F. And then for the beam, you have gamma B. But since the same, ito na lang. Let's just say gamma FB for the floor and beam. So, for WF, we have 6 kN per m cubed multiplied by the area. Now, the area is the spacing multiplied by the thickness. Now, the spacing is 0.3 meters. So, this will be 0.3 meters. And then, our thickness is 25 mm. And so, we will need to convert that into meters so that magka-cancel to. So, times 25 mm multiplied by 1000 mm is to 1 meter. And so, we will not square this one anymore because yung isang dimension natin is already in meters. Ito lang yung kina-convert natin. So, this will give us 0.045. And then, this is kN per meter. Now, this is still for the floor. We still have to compute the weight of the beam. So, WB is equal to 6 kN per m cubed because, again, it's still gamma times area. And then we'll multiply this one by the cross-sectional area of the joist. So that's 100 mm by 150 mm. This is 100, and then this is 150. So this will be 100 mm times 150 mm, and then multiplied by 1 over 1 meter is to 1000 mm, and then we will square this one. So this will be 0.09 kN per m. And so now we already have the answer for letter A, which is this value. Kasi yung tanong is distributed dead load of the floor. And then for letter B, we have the dead load of each joist. And so ito yan. 0.09 kN per m. However, we need the answer in Newton per meter, so we will have to multiply our answers by 1000. So, converting this into N per m, we have 1 kN is equivalent to 1000 N. So, magka-cancel to, and then our answer will be 45 Newton per meter. And then, doing the same dito, we have 0.09 times 1000, which will give us 90 Newton per meter. Now, the next question is to compute the total distributed dead load that each joist will carry, including itself daw. And so we will include the weight of the joist. And so to get that, let's just say W total, we will add the distributed weight of the floor and the distributed weight of the beam. So this is WF plus WB, which will give us 45 N per m plus 90 N per m, which is 135 Newton per meter. And so effectively, our beam will carry this distributed load. Yan. Instead of analyzing it by parts, by slab and then by beam, we have this equivalent loading, which is W total. And so when we are analyzing this one, let's say this is simply supported and then this is also simply supported, then ito na yung total load natin. And so let's try to check our answers. Diba, we have 45 Newton per meter for the floor, 90 for the joists, and then if we add both of them, we have 135 Newton per meter. And so next, we have now a 150 mm thick concrete floor supported by steel joists spaced at 2 meters on centers. And then each steel joist has a cross-sectional area of 4,500 mm squared. If concrete weighs 23.54 kilonewton per m cubed and steel weighs 77.01 kN per m cubed, we have to find the uniformly distributed dead load each steel joists carry, including itself. So again, what we are looking for is W total because we are including the beam weight, including itself kasi. So W total is equal to W beam plus WF. Again, these are just using gamma times area. So W total will be, for the beam, we have this unit weight because again, our joists are made of steel. So we will be using, for the beam, this unit weight. And so this will be 77.01 kN per m cubed multiplied by the area of the beam, which is 4,500 mm squared. Again, this is the cross-sectional area of the joist. And so this will be 4,500 mm squared, and then we will multiply this by 1,000 mm is to 1 meter, and then we will square this one. And so this will give us, this is still for the weight of the beam. We have to add the weight of the floor. And so this will be plus, we will now be using this unit weight because the floor is made of concrete. And so we have gamma, which is 23.54 kN per m cubed multiplied by S times T. Again, our beam may look like this. Let's say this is the steel joist, and then this is the portion of the floor carried by this joist. And so this will be, again, this is the thickness of the floor, this is the spacing, and then this is made of steel, and this is made of concrete. And so this area, which is the cross-sectional area to be used for the weight of the flooring, that's S times T. And so this will be S, which is 2 meters, multiplied by the thickness, which is 150 mm. Now we have to convert that one into m. So 150 mm times 1 over 1000 mm is to 1 meter. That will give us 7.41. And then this is in kN per m. And then this is W total. And so let's try to check our answer. Now we have 7.41. However, these were also solved. And so let's try to check. Considering this one, the weight of the beam, we have 0.347 kN per m. And then for the floor, we have 7.062 kN per m. And so let's try to check. The same lang dito. And so tama yung solutions natin. Now, aside from dead loads, we also have live loads. Now again, this is due to occupancy or the furnitures, chairs, tables, bookshelves found in our offices or libraries. And then usually, meron tayong codes na ginagamit dyan. Now this acts over an area because what's usually given is the intensity of the live load, which is in kN per m squared or kPa. So that's why this acts over an area instead of just a uniformly distributed load. Kasi ito, kN per m, if itong naka-red. However, if it acts over an area, which is this one, ito, kaya magiging kN per m squared, which is kPa. Kasi again, I is usually given in kPa. Now usually we want this load, this one, in kN per m. Now to get that, we have to multiply I by S, not L. Because we are usually considering the long side or essentially the longer span, because let's say this is L, ito. If I will multiply this by L, then I will be able to get this uniformly distributed load. However, this is not my interest because this distributed load acts over the spacing or dito. We are interested in the distributed load that acts over the span or the length of the beam. And so ito yan. Again, hindi ito yung interest natin kasi hindi naman ito yung beam natin. This is our beam. Ito. Let's say, ito yung x-ray niyan. Diba? Ito yung length ng beam. So, erase ko to. And then, meron tayong figure for you to internalize why we are multiplying this by S. Kasi diba, we have kPa, which is kN per m squared. And to make this kN per m, we will just multiply this by isang dimension. Kasi diba, if we multiply this by meter, then we will have kN per m. However, we are multiplying this by S to get this distributed load. Because if we will multiply this by let's say L, we will get this load, yung kanina. Again, this is not what we are interested in. So ito yan. If we will multiply by L instead of S, ito yung mangyayari. We will multiply this one by L, then we will get this one. Itong nasa gitna. This is essentially the resultant. But again, that acts over the spacing, hindi over the span of the beam. And so this is wrong. Ito talaga yung mangyayari. Again, dito mag-a-act yan, along S. However, if we will multiply by S, then we will get this resultant. Diba? Kasi this is the area, the intensity in kPa, and then multiplied by this dimension, we are essentially getting this one. And so we already have our distributed load acting over the length of the beam. And so that's what we are interested in. And so if ito na lang yung isusulat natin, magiging ganito. This is what we are going to analyze. And then, this is already in kN per m, and then usually our beams are simply supported. So meron tayong reactions dito at each end. And so let's try this problem. A floor system that consists of a wooden floor supported by wooden floor joists spaced at 0.25 m on centers. If live load occupancy is residential, find the distributed live load WLL to be carried by each joist. And also find the reactions due to this live load if the joists are simply supported on a 3M span. Now, given na dito na for residential buildings, kasi again, yung load occupancy is residential, I is equivalent to 1.9 kPa. That's from NSCP. And so, let's try to solve this one. Lalagay ko na lang dito. And so, first, we are to find the distributed live load to be carried by each joist. And so, ito yan. Diba? WLL is equal to I multiplied by S. And so our I is 1.9 kPa, which is kN per m squared. So 1.9 kN per m squared multiplied by the spacing. Yung spacing natin is 0.25 meters. And so this will be 0.25. Now 1.9 times 0.25 meters will give us 0.475. And then this is kN per m. Now, we also have to compute the reactions due to this live load. Ito. Now, if the joists are simply supported on a 3m span, ito yung mangyayari. We have 3 meters, and then this is simply supported, and then we have WLL equal to 0.475. So this will be 0.475 kN per m. And so to compute for these reactions, dito saka dito, we can simply get the resultant and then divide the result by 2. Kasi symmetrical lang yung beam natin. Symmetrical yung loading, and then yung supports are at each end. So the resultant of this one will be 0.475 multiplied by 3, which is 1.425, and then this is kN, and then dividing that by 2, we have 0.71 dito kN, and then dito rin. And so this is our answer for letter A, and then this is our answer for letter B. And so let's try to check. Our distributed live load is 0.48, and our reaction is 0.72 kN. And so tama yung solution natin. Now, the problems that we have solved earlier were treated as one-way slabs. However, in reinforced concrete design, we will first evaluate if our slab is one-way or two-way. And so ito yung definitions natin. A one-way slab is a slab supported on two opposite edges only, or on all four edges, but the ratio of the short span to long span is less than 0.5. It is called a one-way slab since the bending occurs in one direction only, and it's along the shorter span. So this is what will happen. If S over L is lesser than 0.5, that's a one-way slab. However, this is the condition if your slab is supported on all edges. If it's only supported on two edges, then it will automatically be a one-way slab. Now, how will this look like? Let's say you have this slab and then it's supported by two beams. If we will apply a load dito, then it will bend this way, pa ganyan, this one. Because nandito kasi yung supports. This part will not bend. Ito, saka ito. Only this one. Because this is the portion of the slab that is simply supported. However, if S over L is lesser than 0.5, then it won't matter if it's supported on all four edges. It will still be a one-way slab. Kasi diba, if your S is small, and then your L is very large, then malaki talaga yung chance na magbe-bend dito yung slab natin. Kasi masyado tong mahaba. Again, let's say this is our S, itong side na to, and then this is L. Notice that this dimension is significantly larger than this one. And so, even if meron tayong supports dito, our beam will naturally bend this way, pa ganyan. Mahirap mag-bend dito kasi the span is very small. And so, magiging ganito yan. Yan. As you can notice, the bending is along the shorter direction. When we say along, it's parallel. Diba? This is the bending, and then it's parallel to this one, the shorter side. Again, this is the longer side, and then this is the shorter side. And so now, let's try to solve this problem. The floor of a building shown is subjected to the following loads. The superimposed dead load is 2.8 kPa. Again, this is the dead load excluding beam or girder weight. Kasi yung superimposed dead load, that usually entails objects that are fixed with your beam. Now, we will treat this the same way as the live load intensity, in which we will multiply this load in kPa by the width of the tributary area. So recall that WLL was equal to I times S. And then if we will solve this one, then we have W superimposed dead load is equal to I times S pa rin. And then our superimposed live load is 6 kPa. And then meron tayong iba't ibang weights for our beams. We have CD and EF equal to 86 kg per meter, and then AB, GH, AG, and BH equal to 97 kg per meter. Now, these are different because most likely, ito yung girders natin because it weighs larger. And then, this will be our joists. And so now, let's try to check. Meron pa pala tayong mga given. We have the concrete slab thickness equal to 100 mm and the unit weight of concrete equal to 24 kN per m cube. And so again, this is the generalized figure of our system. We have our slab, and then the slab is supported by beams, and then itong beams are nakapatong sa girder, or usually naka-weld yan, or it's fixed with the girder. And then itong girders are supported by the columns, itong dalawa, saka ito, and then the columns are supported by the footing. And then finally, the footing is supported by the soil. So essentially, yung soil talaga yung nagki-carry ng lahat ng loads natin dito. But again, since we are transmitting, this is our slab, and then the load of the slab is carried by the beam. Itong beams natin, AC, E, and G, and then the loads of the beam will be carried by the girders, which are your larger beams. And then the load of the girders will be carried by the columns. That's why usually sa analysis natin, in columns and footings, we are cutting this one and then we have a load dito, usually. Now this load comes from all of these. Itong girders, beams, and slabs. However, yung ginagamit dito is yung equivalent concentrated load. And so yan yung load transmission natin. Now, itong figure na to is ang side view. However, hindi natin usually ina-analyze yung loads natin this way. Usually, we are considering the floor framing plan. So, we are viewing this from the top. And so, magiging ganito yan. Tingnan natin yung animation. Yan. Again, these are your beams. Itong naka-apricot. And so, ito yan. This is our beam. Ito, beam. This is a beam. And this is a beam. Kaya, this is ACEG. On the other side, it's BDFH. Hindi lang natin makikita dito. Yung makikita lang kasi natin sa cross-section are the following. Itong ACE and G. And then itong brown is the girder. So, ito yan. Diba? These are our beams. And then itong brown, these are our girders. Kasi itong loads na kinikarry ng beam are carried by the girders. And so, that's why yung CD saka EF is 86 kg per M. So, ito yan. 86 kg per M. And then, ito rin. Now, these way less because these are interior beams. And then yung AB, GH, AG, and BH are 97 kg per M. Now this is because girders kasi natin to. And so it will significantly weigh more. Now this is our slab. Ito naka-gray. And since it's supported on all four sides, ito, saka ito, and then ito, saka ito, then our consideration will be using M is equal to S over L. We will check if it's lesser than 0.5. Now itong 2.5, this is our S, or the shorter side. And then itong 6 meters is our L, or the longer side. So this is L. And so M is equal to S over L, which is 2.5 divided by 6, which is 0.42. And so this is lesser than 0.5. And so we will treat this one as a one-way slab. Now sir, what is the significance of determining whether it's a one-way slab or two-way slab? Now itong type of slab, it determines the tributary area of the beam. Now, if one way yung slab, then automatic na yung kinakarry ng isang beam will be half ng adjacent slab. So, for example, we have beam AB, ito, it will carry this portion. Let's divide this into 2, and then ito yung slab na kinakarry niyan. This is the tributary area for beam AB. And then if we will consider beam CD, then it will have 2 adjacent slabs. However, it will only carry half of each side. So, half dito, and then half din dito. Let's draw a line dito. And since this is also adjacent to CD, then CD will also carry this one. So this whole portion is the tributary area of CD. And so let's just proceed to the next slides. Kasi andun yung color coding ko. Now, erase ko na lang to. And so now, itong naka-violet, this is the tributary area of beam AB. And then for CD, we have 2 adjacent slabs. So, dalawang half ng slab yung kinakarry niyan. So, itong naka yellow-orange, this will be the tributary area of beam CD. Yan. And then, itong naka-green will be the tributary area of beam EF. And then, finally, this remaining portion will be the tributary area of beam GH. And so, ito yan. Tributary area of EH. Now, sir, what is this one? This is our column. Kasi again, we are viewing this from the top. Yung iba kasi, if they are shown the flooring system or the floor framing plan, ina-assume nila na this is the ground floor and then this is the second floor and this is the third floor, which is mali. Again, we are viewing from the top. And so now, for beam AB, let's try to look at this from the lateral view. So, ito na yan. Check natin yung animation. Again, this is the portion carried by beam AB. So, ito yung dimension na yan, 1.25 meters. And then, itong 1.25 is just half ng 2.5 because again, this is 2.5, the spacing, and then half niyan is 1.25. Now again, this is our slab, itong gray, and then this is our beam. This is A, and then on the other side is point B. Now, we have to compute now the total uniformly distributed service load in Kn per M on beam AB and GH. Now, bakit AB and GH? Because they are symmetrical. If we analyze the weight carried by beam AB, then we will also be able to obtain the load carried by GH because they are opposite to each other. And then since our floor framing plan is symmetrical, then we can assume that AB and GH will carry the same load. And so ito yung load computations natin. Let's try to solve the uniformly distributed weight of the slab and also the beam. And so ito na yan. Now again, isusulat ko yung mga given. Our superimposed dead load or WDSI is equal to 2.8 kPa. And then our superimposed live load or WLSI is 6 kPa. And so first, we will compute the uniform dead load, which is equal to I multiplied by the width of the tributary area. Now this is the width of the tributary area. This 1.25 meters. And then for the uniform dead load, for the superimposed load, we have 2.8 kPa or kNm squared multiplied by the width of the tributary area, which is 1.25 meters. So this is 1.25. And so this will give us 3.5 kN per m. And so dito galing yan. And then for the uniform live load, we have 6 kPa multiplied by the width of the tributary area, which is still 1.25. So itong 7.5, this comes from 6 kPa multiplied by the width of the tributary area, which is 1.25 m. And so kaya this is 7.5. And so again, dito galing yan. Now aside from these superimposed loads, we also have the self-weight of the beam and also the self-weight of the slab. So we will compute for that one. For the weight of the beam, we are given that beam AB weighs 97 kg per meter. So this weighs 97 kg per meter. And then in order to convert kg into Newton, then we will multiply it by the gravitational constant, which is 9.81 meter per second squared. Because itong kg times m per s squared will become Newton. And so we will convert Newton into kN so that our units will be consistent. So that's why we are dividing this by 1000 newtons. And so we will have 0.952 kN per m. And then this is the weight of the beam. And then for the weight of the slab, we need the unit weight of concrete and the area of the cross-section. And if we multiply them both, then we will get the weight of the slab. Now the area of the cross-section is simply 1.25 multiplied by the thickness, which is, again, given in our problem, 100 millimeters. So this is our T, which is 100 mm. And so that's why we are converting this into m so that our unit will be m squared. And then our unit weight of concrete is equal to 23.54 kN per m cubed. And so itong 3, this just comes from 23.54 kN per m cubed multiplied by this area. So this is 0.125 meter squared. 24 pala yung nasa given. So erase natin to. This is 24 and then this is also 24. So 24 times 0.125, again, in our given, Y concrete is equal to 24 kN per m cubed. And so this will be 3 kN per m. And so yung total weight ng beam AB, yung uniformly distributed na load, will be equal to the superimposed dead load plus the superimposed live load plus the weight of the beam plus the weight of the slab. And so we are essentially adding 3 and then plus 0.952 and then plus 3.5 and then plus 7.5. And so that's why we have this value. And so let's try to look at our beam. Ito na yan. Diba? This is beam AB. Ito, this is A, and then on the other side, that's B. And so ito na yan. If we will look at it from the side, along the span of the beam, ito yung beam AB natin, and then yung length niya is 6 meters. And then yung total load na kinikarry niya is 14.952 kilonewton per meter. So ito na yan. This is the distributed load. And then we have a resultant for that one, which is just equal to 14.952 multiplied by 6. And so that will be 89.712. And since our beam is symmetrical, then yung reaction dito at A and reaction at B will be equal lang din. And then that will be half of the resultant load. And so ito na yan. These are the reactions of your beam. And then summing of forces vertical, we can just simply say that if we divide this by 2, then ito na yung reactions na yan. So 89.712 divided by 2 will give us 44.856. Dito lang galing yan. Again, this is the condition by symmetry. And so diba, ito yung beam reactions natin. Now, if we will transmit that doon sa girders natin, then these reactions will act downward na. Because again, this support is provided by the girder. So kung titingnan natin, ito na yan. Diba, our beam will have a uniformly distributed load, beam AB. And then, it will have its end reactions. Now, yung end reactions are provided by girder BH and girder AG. Kasi diba, itong beam, nakapatong yan dito. And so that's why yung beam reactions natin will be transmitted dito sa girders natin. And since equal lang yung load ng AB sa GH, then we can say na yung loads dito are still 44.856. And so, ito na yan. This will be the concentrated load transmitted from beam GH and beam AB onto the girders. And so now, let's try to solve for these reactions. Kasi meron din kasi to dito considering beam CD, and then we also have reactions dito for beam EF. And so ito na yan. Let's consider TCD. Again, this is 1.25 and this is also 1.25 because half ng adjacent slab yung kinakarry ng beam natin. And so if we will look at this sa cross-section, para lang yung magiging T. Kagaya nung sinolve natin kanina. So, ito na yan. This is our slab and then this is our beam. Now, this is C. And on the other side, that's point D. So this is our beam. Now this is the superimposed dead load. And this is also the superimposed live load. Now again, this is 6 kPa. And then yung width ng tributary area is 2.5. And so kaya this is 7 and this is 15. And then yung weight daw ng beam natin is 86 kg per m for beam CD and EF. So, this is 86 and we will convert this into Newton. So, we will multiply by 9.81 and then we will divide by 1000 to convert it into Kn per m. And so, we will have 0.844. And then for the weight of the slab, we have the cross-sectional area of the slab, which is 2.5 times the thickness, which is 100 mm, which will give us 0.25 m squared. And then we'll multiply that to the unit weight of concrete. And so, ito na yan. This is again 24 and then this is 0.25 and so this will be 6. And so to get the total distributed load acting on beam CD, we have the superimposed dead load and live load plus the beam weight plus the weight of the slab, which will give us 28.844. And so now let's try to view this from the side along the span of the beam. So ito na yan. This is beam CD. Ito. And then ito yung total load na kinikarry niya. And so this is the distributed load, and then we have a resultant for that one, which is equal to the uniformly distributed load multiplied by the length of the span, which is 6 meters. So this will be 28.844 times 6, which will give us 173.064. And then to get the reactions dito, ito saka ito, then we will just divide this by 2 by symmetry. And so we will have 86.532 for each of our ends. And so this will be 86.532 and then ito rin. And so let's transmit this support reaction onto the girders. And so ito na yan. The end reactions dito sa beam CD are transmitted dito sa girders as concentrated loads. And since our floor framing plan is symmetrical, again, what's carried by CD is also carried by EF. And so if this is 86.532, then this is also 86.532. And so ito na yan. Now again, these are both 86.532. And then, meron din tayong reactions dito. Now, this is equal to 44.856 according to what we have solved earlier. So, this is also 44.856. And then Kn. And so, if we will consider girder AG, ito, then we will include the weight of the girder AG plus itong mga concentrated loads. Ito, saka ito. And then, they will act at their corresponding points. And so, ito na yan. This is our girder AG. Again, let's look at the animation. Ito yung pag-transmit ng loads. Now again, itong blue are simply the reactions dito sa A saka G. And so ito na yan. This is our girder AG. And then the length is equal to 7.5 meters. Now that just comes from tatlong 2.5. Kasi again, this is 2.5, this is also 2.5, and also this one. And so that's why 7.5. Lagay ko na lang dito, 7.5 meters. So going back, we can get the reaction dito sa G, saka dito sa A. Kasi yan na yung i-carry ng columns natin. Kasi diba, we solved the reactions from beam A, B, C, D, EF, and EH. And so, ito na yan. And then, since na-solve na natin yung reactions, we will transmit that dito sa girders. And then, once we solve the reaction of the girders, yan na yung matatransfer dito sa columns natin. Itong column A, column B, column H, saka column G. Now, yung weight ng girder natin is 97 kg per meter. So, this is 97 kg per m, and then we will multiply by 9.81, and then convert that into Kn per m. And so, we have 0.952 Kn per m. That's still the weight of the girder, or this is simply just the weight of the beam according to our solution kanina. So again, these are the loads, and then we have our end reactions dito, one at G and isa dito sa A. Now we won't have to solve the slabs dito kasi itong loads na to, itong 86.532, 44.856, that comes from the weight of the slab of our flooring system according to the tributary areas. And so that's why yung distributed load lang natin is yung weight ng beam. Yung self-weight ng beam. Now, yung resultant dito will be the total loads, including itong resultant ng distributed load. So, this will be dalawang 44.856 and then plus dalawang 86.532 and then plus 0.952, which is the distributed load, multiplied by the span, which is 7.5 meters. And so ito na yung total load na kinicarry ng beam if we will convert it into a concentrated load. And then to get our reactions, we will just divide R by 2. And so ito na yan. Dalawang 44.856 plus dalawang 86.532 and then plus the resultant of the uniformly distributed load caused by the self-weight of the beam. And so that will give us 269.916. And so dividing that by 2, we will get the reaction at G and the reaction at A, which will be 134.958. Again, this just comes from 269.916 divided by 2. And so ito na yung reactions natin sa point A saka point G. And then again, these are the girder reactions. And then we will transmit these patungo sa column. Kasi 'di ba, ito na yan. And then since our system is symmetrical, then itong column H saka column B will carry the same concentrated load dito sa A saka G. And so ito na yung load na ita-transfer natin sa column natin. So if we will look at it from the side, ganito na yan. Again, 'di ba, this is the girder and then ito na yung reaction yan. And then this is the column. And so ito na yan. Itong green comes from the girder. And then we will transmit that to the column. So, kaya ganito na yan. Notice na ito yung usually nakikita natin sa reinforced concrete and our other design subjects. And then if we will try to view the soil as a support reaction, ito na yung mangyayari. Diba, our soil will have a uniformly distributed reaction. So, this comes from the soil pressure. And so, ito na yung transmission of loads. In our video for today, we will proceed to the analysis of two-way slabs. Previously, we have discussed the tributary areas and the load computations of only one-way slabs. So, itong two-way slab is a slab supported on all four edges and the ratio of the short span to long span is greater than or equal to 0.5. It is called a two-way slab because bending occurs in both the short and long directions. Now, let's first recall the bending of one-way slab. Again, it occurs along the short direction dito. Now, itong two-way slab will have supports on all four edges. So, isa dito, and then another support dito, and on the other side. And then yung ratio daw of the short span to long span is greater than or equal to 0.5. And so, since along this span, it's simply supported, it will bend along this direction. And since along this span, it is also simply supported, it will also bend about that direction. And so, yung bending natin, instead of along one direction only, magiging two directions na. And so, it will look like a dish. Try to think of a bowl. So, ito na yung itsura. Magiging ganito yung bending. Paganyan. And so, essentially, mayroong bending dito and also bending dito. So, it will look like a dish. And then, the bending is along the short direction and also the long direction. Now, sir, what is going to change if two-way yung slab? Yung mag-change is yung tributary area. Now, di ba, if one-way slab, we will only consider the adjacent slabs and then we will take half of that slab. However, dito, sa two-way slab, ito na yung tributary area natin. Instead of tig half ng adjacent slab, we will actually consider this triangle. Now, we will use this one if our M is exactly 1 because this tributary area will occur when our slab is a square. Kasi diba, M is equal to S over L. Now, if S and L are the same, diba, yung M natin magiging 1 when our slab is a square. And so that's why for this configuration, we will be using this tributary area. Now, sir, ano yung angle nito? That's 45 degrees. Itong dalawa. Now, this is only triangular because our slab is a square. If our slab is not a perfect square, then this tributary area will be a trapezoid. Kasi ito kasi yung mangyayari. For example, we have this one. This triangle will be formed along the short span. So, if this is the short span, we will form a triangle dito and also dito. And then, let's say this is the long span. Itong dalawa. We will connect the vertices of these triangles and so, magiging ganito. And so, yung tributary area ng short span will be this area. And then, ito rin. And then, for the long span, we will actually consider this tributary area. Itong trapezoid. And also this one. Now, dito, since square, yung dalawang sides natin are the short span. And so, that's why triangle lang lahat to. Now, if M is greater than 0.5 but lesser than 1, ito yung mangyayari. And so, instead of this configuration, magiging ganito yung figure natin. We will have 45 degrees dito and also dito. This is 45, this is also 45, and also this one. And since this is 45, and then this is 90 degrees, this will also be 45 degrees. Ito na yung tributary area natin. And so now, let's try to find this dimension. Ito. Now, if we will divide this triangle into two parts, then we have two right triangles. First, we can draw a dividing line dito. And so, diba, yung legs ng 45-degree triangle will be equal. And so, since we are dividing this one, this distance will be half ng s, which is, let's say, s over 2. Now, ito yung first leg, and then ito yung second leg. And since yung legs are equal, this distance will also be s over 2. So, this is s over 2. And also this distance. This is s over 2. Now, to get this distance, we have L minus dalawang s over 2. And so now, this will be L minus dalawang s over 2. And then, itong 2 magka-cancel. And so, this will just be L minus s. I hope agree tayo dito. Now, I am writing this one because we will be using this in our succeeding calculations. Kasi diba, yung area ng trapezoid natin will be a plus b divided by 2 multiplied by the height. Now, our a will be this distance, which is L. And then our b will be this distance, which is L minus s. So, L plus L minus s, and then divided by 2 multiplied by h. Itong h will be this distance. Yan. And then that's equal to s over 2. So, this is essentially L plus L minus s divided by 2 and then multiplied by s over 2. And so, this will reduce into 2L minus s divided by 2 times s over 2, which will further reduce into 2ls minus s squared divided by 4. And so, kung magaling kang mag-memorize, you may use this formula for the tributary area along the long beam. So, this is the area of the trapezoid. And so now, let's consider real examples kung saan natin makikita yung tributary area na to. And so, this will occur when we have this floor system. Now, let's try to check. Again, this will happen when our slab is a perfect square. But if it's not, it will look like this. And so, if we will see this in action, ito na yan. Diba, this is a square. And so, yung tributary area natin will consist of 4 triangles for this slab. And then for this slab, we have the long side equal to 6 and the short side equal to 4. And so, M will be equal to S over L. Now, our S is the short span, which is 4. And then divided by the long span, which is 6. Now, 4 over 6 will be 2/3, which is 0.66. And then, diba, yung 0.66 is greater than 0.5. And so, this is a two-way slab. And since two-way, hindi na half ng adjacent slabs yung ika-consider natin. Instead, we will be using this tributary area. Now, if we want to consider beam AE, then our tributary area will be itong naka-blue. And then, if we want the tributary area for beam AB, then we will consider this one. Ito. Kasi isang side lang yung adjacent. And then, if we want to consider the tributary area of beam BF, then we will add itong dalawang blue areas. Kasi this is for the left adjacent side, and this is for the right adjacent side. So, we will essentially add both of these areas. Now, this is unrealistic, no? And so, let's just say this is 1 meter. So, bakit naging 7 to? Now, sir, what if I will consider beam OP? Hindi automatic na gagawin mong two-way slab. You still have to check M first. So, if we will consider beam OP, then our M will be S over L. And then our S will be itong shorter span. I mean, the shorter side of the slab. So, that's 1 meter. So, this will be 1, and then our L will be the longer side. And so, it's 8 meters. Ito. So, this will be 1 over 8, which is 0.125. And so, diba, this is lesser than 0.5. And so, yung tributary area natin for OP will just be half ng slab. So, magiging ganito. Yan. And then, we will only consider this area. And so, ito na yan. This will be our tributary area for beam OP. And then, sir, what if I will consider KL? We have to check yung M for this adjacent slab and also the M for this adjacent slab. Now, for this adjacent slab, we already know that we will just be considering half of the slab because M is lesser than 0.5. So, for this side, we will just consider half nito. And then for this panel, we will be considering another M. So, our M for this one will be, our S will be the shorter span, which is 6. So, 6. And then, our longer span is 8. And so, ito na yan. 6 over 8 will reduce into 3/4, which is 0.75. Now, this is greater than 0.5. And so, this will be two-way. Now, sir, diba two-way? What will be this area? Will this be triangular or trapezoidal? This should be trapezoidal. Now, bakit? Now, that's because beam KL is along the longer span. Kasi diba, it's along 8 meters. And so we will consider a trapezoidal area for this one. Yung triangular will just occur along the shorter span. And so that's what you have to remember talaga. And so if we will draw the tributary area of beam KL, we will have this one. First, we will consider half dito. And for this adjacent slab, we will be considering this trapezoidal area. Itong naka-green. And then, sir, what if gusto ko yung FG? Ano yung itsura? Now, we will first check M. Diba dito, this is a two-way slab. And so, for this adjacent slab, we will have a trapezoidal area. However, for this adjacent slab, we have a square. Kasi diba, this is 6 meters, itong side na to, and then this is also 6 meters. And since that's a square, diba, yung tributary area natin will be triangular. And so, ito na yan. Magiging ganito. This will be the tributary area for this adjacent slab. So, magiging ganito. And so, essentially, our tributary area for beam FG will resemble a diamond. Kasi we will be considering this whole area. Yan. Bale, trapezoidal plus triangular. And so, yan yung analysis natin dyan. Now, so that we can internalize the concept, we will try to solve a problem. Kasi solving problems is what builds retention talaga. If you will just learn the concept and then you won't solve problems, you will not be able to master the topic. And then there's also a big chance that you will just forget everything that you have learned. And so for our problem, we have a concrete floor plan with 180 mm thick concrete slab supported by 250 mm by 500 mm concrete girders. And then it is cast monolithically with the slab. Now, the occupancy or use of the area is library reading area. And so, ibibigay ko na lang yung value nito for the intensity, which is from NSCP. And then, if concrete weighs 23.54 daw, determine the following. We have to find out the uniformly distributed dead load of the indicated short and long beams, the uniformly distributed dead load of the concrete slab to be carried by the short and long beams, and then the equivalent uniform live load, and also the total uniform load. Now, ito yung itsura ng floor system natin. Now, lahat ng short sides are 5 meters, and then lahat ng long side is 6 meters. And so if we'll compute for M, diba, this will be S over L, which is 5 divided by 6. Now 5 over 6 is 0.83. And so diba, this will be a two-way slab because this is greater than 0.5. So magiging two-way. And since two-way, then we will have a trapezoidal area along the longer span and a triangular area along the shorter span. Now itong dalawa, this one and this one, these are the indicated short and long beams, and so we will be solving for the loads na nandyan. Now for this beam, we have two adjacent slabs that considers a triangular area kasi that's along the shorter side. Again, this is the short beam, ito, and then this is our long beam. For the long beam, we will be considering a trapezoidal area, and so let's try to isolate this slab. And so magiging ganito. Now again, this is the short beam, which is this one, and then this is our long beam, which is this one. Now again, this is our short beam, and then this is our long beam. We will essentially be considering this area. Now I will first explain kung ano yung shortcut formulas na gagamitin natin. Kasi hindi lang kasi tayo magsasum up ng forces vertical. Mahirap tong i-derive because what we are considering is the moment at the midspan. For example, for this beam, we are interested in the moment dito and also dito. And then, dyan galing yung shortcut formulas natin. And so, I will be explaining that. And so now, ituturo ko sa inyo kung paano na-derive yung shortcut formulas natin for the dead load and live load computations within the slab. So, first, let's go back dito. Diba, yung uniform load natin will be the intensity of the dead or live load multiplied by the width of the tributary area. And so, we will first have to compute kung ano yung magnitude nito. Now, nilagay ko na dito, it's WS over 2. Now, itong LB per feet, this should be KN per M. So, ilalagay ko na lang. This is KN per M and also this one. English kasi yung units ng book na ginagamit ko. Now, if we will look at our floor system, for this triangular load, we will consider this area. Now, sir, ano yung width ng tributary area na gagamitin namin? Diba, this is S. Itong 5 meters. And then, itong 6 meters, this is our L. And then, diba, this angle is 45 degrees. Zoom in tayo. This is 45. Now, again, if we will draw a line dito, then we can form a 45-degree triangle. And then, diba, yung legs niyan are the same. So, this distance is half ng S. Kasi, diba, this is S. So, this will be S over 2. And so, this will also be S over 2. Kasi ito yung dalawang legs. Ito, saka ito. And so that's why yung value ng load natin is WS over 2. Now, don't be confused dito. Itong W kasi, this is just the intensity of the load in kPa. So, let's make it clear dito na this is in kPa. Para lang itong yung I natin. Again, balik tayo. Diba, ito yung ginamit natin for the uniform live load, which is the intensity in kPa multiplied by the width of the tributary area. And so, the same lang yan dito. However, instead of I, W yung ginamit dito because it's much more intuitive kasi. Again, W is the intensity and then itong S over 2, this is the width of the tributary area. And so, that's why this is the value of our uniform load. Now, again, balik tayo dito. This is the width of the tributary area, which is S over 2. Now, yung next na gagawin natin is we should convert the actual load into an equivalent loading. And then, kailangan na the same yung moment at the midspan of these two configurations. And so, first, let's solve for the moment at G dito sa midspan considering the actual load. And so to compute for that one, we need the support reactions. Now since our beam is just simply supported and then symmetrical yung loading, then we will just find the resultant and then we will divide it by 2. Now this triangle will have a resultant dito sa gitna. And then this value will be the area of the triangle, which is diba 1/2 times base, which is S, and then multiplied by the height, which is W times S over 2. So this is our height times W then S over 2. Now sir, bakit S to? Again, let's go back to our figure. This is the base because we are considering this beam. And then this whole distance, ito, is S. And so now, this will reduce into WS squared divided by 2 times 2 will give us 4. And so yung reaction dito sa A saka C will be half ng WS squared over 4. And so that will be WS squared divided by 8. So let's say RA is equal to WS squared over 4, which is the resultant, divided by 2. And then this will give us WS squared divided by 8. And so ito na yung reaction natin at A. And so erase ko na lang to. And then let's just use this one. Now to get the moment at G, we can make a cut at this point. And then we will take moments about dito sa midspan. So if we will cut this into half, diba meron tong resultant. This right triangle. And so yung resultant will be located dito. And then the value of this one will be the area of this triangle. So that will be 1/2 times the base, which is, diba, this is S, yung whole distance, and so this is S over 2. And so yung base is S over 2, and then multiplied by the height, which is WS over 2. And so this will be WS divided by 2. And so this will give us 2 times 2 times 2. This will be 8. And then WS times S will give us WS squared. And so now we will be able to compute the moment dito sa G. Now sir, what is the moment arm of this resultant force? Diba, we are considering patungo sa G, so it will be this distance. Now this is 1/3 of S over 2. Kasi diba, this whole distance is S over 2. And since yung centroid ng triangle is 1/3 patungo sa height, yung centroid niya, this will be S over 2 times 1/3. Now that will give us S over 6. Kasi diba, 2 times 3 is equal to 6. So this is, dito na lang, this is S over 6, yung moment arm. And so taking moments about dito sa G, we have this equation. Mg is equal to Ra times S over 2. Kasi diba, this is our load and this is our moment arm. So this will be WS squared over 8 and then multiplied by S over 2. Now this will cause a clockwise moment about G. And so that's why this is positive. And then for this one, for the resultant of the right triangle, it will cause a counterclockwise moment about G. And so that will be minus. And then yung load natin is WS squared over 8. So minus WS squared over 8 and then multiplied by the moment arm. Now yung moment arm natin is S over 6. And so times S over 6. Now this will simplify into WS cubed over 16 and then minus WS cubed divided by 8 times 6, which is 48. And so yung Mg will be 1 over 16 minus 1 over 48. That will give us WS cubed over 24. So this is WS cubed divided by 24. Now this is the moment at G. And so we have to find itong W prime S. This is the equivalent load. If we will convert this one into a uniformly distributed load, kasi it would be easier to analyze if we have a uniformly distributed load instead of this one. And so that's why we are converting. Now the moment at G should be WS cubed over 24. Now, if you look at this figure, this will have a resultant dito sa gitna. And then that value will be the uniformly distributed load multiplied by the length, which is itong S. And so this resultant load will be W prime S, which is this one, multiplied by the span, which is itong S. And so this is times S. And so since symmetrical yung loading natin, and then it's simply supported, then each support will carry half ng resultant load. And so this will be W prime S times S divided by 2. Now, I hope agree tayo dito. This is just the magnitude of the resultant and we divided by 2. Now, if we will make a cut dito sa G, we can take moments about that point. And if we make this cut, then we have to find the resultant of this distributed load. Now, this will be W prime S multiplied by S over 2. Kasi again, this distance from here patungo dito will be S over 2. And so our moment arm for this one will be half ng S over 2, which is S over 2 times 1/2. It will give us S over 4. And so now we can take moments about G. Now that should be equal to WS cubed over 24. So taking moments about G, we have W prime S times S and then divided by 2 multiplied by the moment arm, which is S over 2. This is for the reaction at A. And then this is positive because it will cause a clockwise movement about dito sa G. And then for this one, this will be minus because it will cause a counterclockwise movement about G. And so that will be W prime S times S over 2 for the resultant load. And then we will multiply that by the moment arm, which is S over 4. And so ito na yan, times S over 4. And so we can simplify this into W prime S times S squared divided by 4. And then minus W prime S times S squared divided by 8. Kasi 4 times 2 is equal to 8. And so this will simplify into 1/4 minus 1 over 8, which will give us W prime S times S squared divided by 8. And so this is the moment at G. Now we need to equate the two. Ito saka ito. And then we will get W prime S or the equivalent load. And so this will be W prime S times S squared divided by 8 is equal to WS cubed divided by 24. Now again, we are just equating itong dalawang mg, ito saka ito. And so let's cross multiply. Diba? This will become WS cubed over 24 and then times 8 sa numerator and then times S squared sa denominator. We have W prime S. And so diba, this will cancel itong 8 saka 24. Now this will be 1 and then this will be 3. And then itong S squared will cancel. And then isang S na lang yung matitira dito sa numerator. And so, diba, yung W prime S natin will essentially become WS over 3. And so, that's why ito yung derived formula natin for the equivalent uniformly distributed load if we are given this triangular area. Now, sa ibang books, this may also be IS divided by 3. Now, depende na yan sa'yo if whichever is convenient. But usually, ito yung ginagamit ko. But I will just take note na itong W is in kPa. So, this is in kPa. And so again, this is the shortcut formula for our short beams because itong triangular load is actually along the shorter side. And then if we have this one, the trapezoidal load, we will still be applying the same concept dito. However, since the process is tedious, nilagay ko na sa MathCAD yung simplification process. And so ito na yan. Now I will just run through the solution. Now itong RA will just be half of the resultant load ng trapezoidal area. And so itong 1/2 times L plus L minus S, this is just 1/2 times A plus B and then multiplied by the height, which is WS divided by 2. And so it will simplify into negative SW times S minus 2L divided by 8. And then we can get the moment at G. This is for the reaction at A. And then this is for the resultant of this triangle, itong a triangle with a base of S over 2. And so that's why that's 1/2 times the base, which is S over 2, and then multiplied by the height, which is WS divided by 2. And then our moment arm will be L minus S divided by 2 patungo dito sa G, itong distance na to, plus 1/3 ng S over 2. Kasi yung centroid niyan is nandito. And then for the last one, we have the resultant of this half distributed load. And so yung magnitude ng load natin is WS over 2. And we will multiply by the length, which is L minus S divided by 2 kasi half lang yung kinoconsider natin. And then our moment arm will be L minus S divided by 4 kasi diba this is L minus S and then itong half is L minus S divided by 2. And so if yung resultant natin is nandito, this will be L minus S over 2 divided by 2 again. And so that's why it will be L minus S divided by 4. And then equating the moment at G for both configurations, we will be able to arrive with this formula. Now in other books, this may also be called I. Now, depende na yan sa'yo. And then, ito na yung derived equation natin. WS divided by 3 and then multiplied by 3 minus M squared divided by 2. And so, let's just copy this one. lalagay ko na lang dito. Now again, this is WL prime because we are considering along the longer side. And then along the shorter side, we have itong WS prime which is WS over 3. And so ito na yung loads natin. Now sir, saan namin to gagamitin? We will be using this one for letter B saka letter C. Now sir, why will we not apply this one dito sa A? Now that's because the uniformly distributed dead load of the beams themselves will not be affected by the tributary area. Kasi diba, yung beam natin, yung self-weight niya is just along the span. It will not consider the tributary area. And so lalagay ko na lang dito, we will be applying shortcuts for this one. And so for letter A, we need to compute the uniformly distributed dead load of the indicated short and long beams. And so ito na yan. This will be our short beam and this will be our long beam. So ilalagay ko na lang to dito. And so now let's just divide our solution. This is for the short beam and then another column will be for the long beam. Now for letter A, we have to compute the uniform dead load or the self-weight of the beam. And so that will be gamma times the cross-sectional area. Now we will label this as WB or the weight of the beam. And so this will be gamma times area. And so our gamma will be 23.54 kN per m cubed and then multiplied by the area of the beam. Now yung area ng beam natin is itong area ng girder. And so ito yung cross section ng beam natin. This will be 250 and then millimeters and this will be 500 mm. And then meron yung slab dito sa taas. And then itong slab na to will be 180 mm thick. However, we will not be including this one in our calculations for the uniformly distributed dead load of the beam. Kasi ito lang yung i-consider natin for the self-weight. Itong area na to. Now sir, bakit yan lang? Now that's because itong weight ng slab is dealt with dito sa B and C by applying the shortcuts dito sa intensities natin. Now again, this area will be 250 mm is 0.25 meters and then multiplied by 500 mm which is 0.5 meters. This will be the area. And so let's just copy this one. Lagay natin dito. And so yung WB natin will be 23.54 times 0.25 and then times 0.5, that will give us 2.9425. And then this is kN per m. And then for the long beam, the same lang yung weight natin. And so let's just copy this one. Ito na yung answers natin for letter A. And then for letter B, we have to compute the uniformly distributed dead load of the concrete slab. So yung gagawin natin dito is we will first compute for the resultant of the slab. Kasi diba yung area natin is pa-triangle. And then we will need to convert that into the equivalent load. And so for this one, I will just correct this one. For letter B, we won't be applying the shortcut. We will only apply that dito sa letter C. Kasi hindi naman kasi intensity yung gagamitin natin for letter B. Dito lang sa letter C. So dito, we will apply the shortcut. However, for this one, we need to first get the resultant load. And then after nyan, we will convert that into a uniformly distributed load. Now sir, how will we get the resultant load? In our one-way slab discussion, yung ginamit natin is gamma times area, so that we can get the uniformly distributed load of the slab. However, for this one, since the area is initially a triangle, then we will just get the resultant load. And then after nyan, we will convert that into a uniform load. And so instead of area, we will multiply by the volume. Kasi diba, this is in kN per m cubed, itong gamma. And then yung volume is m cubed. And then diba, this will just cancel. And so we will have the result in kN. And then this concentrated load is the resultant load. And so once we get this one, we will just divide this by the span of the beam so that we can get its equivalent load. And so instead of WS, I will just label this as RS, or the resultant load of the slab. So this is RS, and so RS will be equal to gamma, which is 23.54 kN per m cubed multiplied by the volume. Now sir, ano yung volume na i-consider namin? Zoom in tayo. We will consider this volume, itong triangle. Now diba, this is S, and then this is S over 2. And so we can compute the area. That will be 1/2 times the base. Our base is S, itong distance na to. And we will just consider one side. So 1/2 times the base, which is S, and then multiplied by the height, which is itong S over 2. Again, zoom tayo. That's S over 2 yung height. And so times S over 2. Now ito yung area ng triangle. And then we will multiply that by the thickness of the slab so that we can get the volume. And so yung thickness ng slab natin is 180 mm, which is 0.18 meters. Now again, yung S natin is meron tayong numerical value, which is itong 5 meters. So this will be 5. Again, this is M, and then itong S will also be 5 meters. And so yung M cube dito, magka-cancel. Saka itong tatlong M. And so yung value nito will be 26.4825. and then this will be in Kn. Now, after nito, we will divide this by the span of the beam para makuha natin yung equivalent uniform load. And so, let's just label this as the weight of the slab. Now, that will be 26.4825 Kn divided by the span of the beam, which is, along the shorter side, 5 meters. Kasi diba, ito yung kinoconsider natin. And so, Ws will be 26.4825 divided by 5 will give us 5.2965 and then Kn per meter. Ito na yung answer natin for letter B for the short beam. And then for the long beam, we will just be using the same concept. So first, we have to compute the resultant. Rs, let's just label this as RSS, or the resultant load of the slab for the shorter beam, and then let's label this as RSL, or the resultant of the slab for the long beam. And so this will still be gamma times the volume. And so yung gamma natin is 23.4 Kn per m cubed. And then yung volume natin is the area of the trapezoid, ito, multiplied by the thickness of the slab. Now sir, why are we considering the trapezoidal load? We are considering that one because we are already interested in the long beam. And so now, diba, we already derived a formula for the area of the trapezoid. Now, ito yan. Diba kasi again, this is S over 2, and then this length is L minus dalawang S over 2, and then multiplied by the height, which is S over 2. Now, this is just the area of the trapezoid, yung general formula. And so, ito na lang yung gagamitin natin. However, if you don't want to memorize this one, then you can just draw the figure. Maybe for now, let's just use the figure, and then let's try to check if we can get the same result using this one. And so I will just draw this one. Now, diba, this is our long beam. This will be 45 degrees, and then let's draw a line dito. And then this is also 45 degrees. Now, diba, this distance is 5 over 2. Kasi diba, this is S, and then this is S over 2, and this is also S over 2. And then this is L, and this is also S over 2. I mean, this is L minus S. Kasi diba, 6 minus dalawang S over 2. So again, our S over 2 will be 2.5 because ito yung S natin. And then our L minus S will be 6 minus 5. And so that will give us 1 meter. Again, this is from 6m minus 5m. And then this distance is also 2.5m. And then our height will be S over 2 then. And so this will be 2.5 meters. And so yung area ng trapezoid will be 1/2 times A plus B. Yung A natin, 6 meters. And then plus B, which is L minus S, which is 1, and then multiplied by the height, which is 2.5 meters. And so this will be 2.5. And so this will give us 8.75 m squared. Now, if we will use the shortcut formula that we have derived earlier, then we can get this value. So, using this one, 2 times L, which is 6, and then times S, which is 5, minus 5 squared divided by 4, we have 8.75. And so, the same lang yung result natin. Now again, this is still the area. We need to multiply this by the thickness of the slab to get the volume. So again, yung volume is the area of the trapezoid, which is 8.75 m squared, multiplied by the thickness of the slab, which is 180 millimeters, which is 0.18 meters. So this is 0.18, and then meters. So this will give us 37.0755. And then this is in Kn. Now this is still the resultant load. We will divide this by the span of the beam so that we will get the equivalent uniform load. And so let's just label this as WSS for the short beam. And for this one, we have WSL, which is equal to 37.0755 Kn divided by the span of the beam. Now, the span along the longer side is itong 6 meters. So, this is 6m. And then this will be 6.17925. And then this is in Kn per meter. And so, this is the uniformly distributed dead load of the slab along the longer span. So, this is our answer for letter B. Now, another consideration is that for this short beam, we actually have 2 sides. And so, yung distributed load natin should be multiplied by 2. Now sir, kailan tayo hindi mag-multiply ng 2? We will not multiply by 2 if we are considering this short beam. Kasi diba, its tributary area will just be isang side. And so, isa lang yung i-consider natin. Now sir, how about for the long beam? When will we not multiply by 2? You will not multiply by 2 if this is the long beam you are considering. Kasi diba, if we are considering this one, then we will only have isang trapezoidal area. However, for our indicated short and long beams, dalawang side kasi yung i-consider natin. And so, for letter B, we'll multiply this by 2 and also this one. And so hindi pa ito yung final answer natin. Kasi again, this just accounts for one side. And since dalawa yung sides natin, this one and this one, then we'll multiply this by 2. So our WSS is equal to 5.2965 times 2, which is 10.593. And then this is in kN per m. Now this is to account for two sides. Yan. And then we will also do the same dito sa WSL natin. So our actual WSL will be dalawang trapezoidal area. And so 6.17925 multiplied by 2. So that will give us 12.3585. And then this is in kN per m. And so again, ito yung actual answers natin. Ito, saka ito for letter B. Now for letter C, we have to compute the uniform live load to be carried by the short and long beams. And so dito na natin gagamitin yung shortcuts na binuo natin kanina. So we will be using itong WS over 3 and WS over 3 times 3 minus m squared divided by 2. So I will just copy this one. This is for letter C for the short beam, and this is letter C for the long beam. Now for the equivalent uniform live load, we will also be multiplying by 2. Kasi again, we are considering two sides. Yung dalawang sides are subjected to live load intensities. And so, we can now solve for this one. However, hindi pa given yung intensity for library areas. Now, this should be 2.9 kPa. This is from NSCP. And so, ilalagay natin to dito. So, our W, again, this is in kPa. Itong dalawa. Our W is 2.9 kPa for our libraries. So, ito na yan. So, for our WS prime, we have 2.9 kPa or 2.9 kN per m squared multiplied by S and then divided by 3. So, our S is 5 meters. So, this is 5m. And then we will divide this one by 3. And so, this will be ito magka-cancel and also ito, and then we will get 4.83 kN per m. Now this just accounts for one side, and so we will have to multiply this by 2 to account for the two sides. Kasi again, meron tayong dalawang sides dito, and so our actual WS prime will be 2 times 4.83, which is 9.66, and then kN per m. And so this will be our answer. Now I'll just remove yung highlight dito so that you won't be confused. And then for letter C dito, dito sa long beam, we have WL prime is equal to WS over 3 times 3 minus m squared divided by 2. Now our W is 2.9 kPa or 2.9 kN per m squared, and then multiplied by S, which is 5m, divided by 3, and then multiplied by 3 minus m squared. Now again, our m is S over L. This is S over L. So this will be 5m divided by 6m, and then squared, and then divided by 2. Now this will give us 5.57, and then kN per m. Kasi again, this will cancel. Ito saka ito. And then this is just on one side. And so we will still multiply by 2. And so our actual WL prime will be 5.57 multiplied by 2, which is 11.14, and then kN per m. And so this will be our answer for letter C. And then for the last question, we have to compute the total uniform load. Now, madali na lang to, because we already have our answer for letter A, B, and C. So for letter D, we'll just add all of them. So for letter D, we have, let's say W total, that's equal to 2.9425 plus 10.593, and then plus 9.66, which will give us 23.1955. And then this is kN per meter. And then for the long beam, we have WT is equal to 2.9425 plus 12.3585, and then plus 11.14. And so this will give us 26.441. And then this is kN per m. And so now we already have our answers for all of the questions. Now again, recap lang tayo. For the weight of the beam, we will just simply use gamma times area because it is unaffected by the tributary area. And then for the weight of the slab, we need to first get the resultant, and then once we get the resultant, we will divide it by the span of the beam para makuha natin yung equivalent uniform load. And then since it only accounts for one side, we will multiply by 2 para we can get the total load considering the two sides. And then, the same lang yan dito. However, yung area dito will be yung area ng trapezoid. And then, yung area dito will be the area of the triangle. And then, don't forget na you should multiply by the thickness of the slab. And then, for letter C, we are essentially just applying the formulas na na-derive natin earlier. And then, we are still multiplying by 2 because it only accounts for one side. And so, that's why multiply tayo ng 2 dito and also dito. And then, for the total load, we will just add the weight of the beam plus the weight of the slab and the live load. And so, kaya ito na yan. And also dito. And so, ito lang yung mga considerations na dapat mong tandaan if you are dealing with two-way slabs. Now, I hope nakatulong to sa inyo.